This video introduces the idea of optimal strategies in biology in the context of what could be analyzed using basic calculus. In biology, organisms often have a particular moment when they switch behavior, and the time of transition often has an impact on the individual's success. For example, a plant might grow and grow and grow, and the bigger the plant gets before it reproduces, the more potential it has for seed. But at the same time, the longer it waits, the bigger the chance it has that it's going to die. And if it dies, it doesn't produce any seed. And so a plant has to be able to have some threshold of time at which point it's going to determine that it will set its seed, as opposed to continue to just get bigger and bigger, running a risk of not being able to do anything. Similarly, animals often have to go searching for food. So for example, I might have a bee that's going and collecting pollen, nectar from flowers, and it's going to go to an individual flower and spend some time gathering, exploiting the resources on that flower, and then it's going to travel to another flower. Now the question that the bee has to ask is, how long should it spend collecting at an individual flower? The longer it collects, the less it gets. But it also, you don't want to spend too short a time because you want to get as much as you can. So there's another question. What's the right time that the bee should spend gathering food at an individual plant? And this could be not just a bee, but any animal that has to make a decision about how much time to spend exploiting the resources when it has some sort of commitment or time that it takes to go from one resource to the next. Let's start by talking about the challenge of growth versus reproduction. So if I'm this plant, I have a picture of an agave plant, and it wants to grow. The idea is that if it waits too long, it's going to die. So this is our first factor. We don't want to wait too long. On the other hand, the longer we can spend growing, the more we'll be able to produce body mass so that we have more energy to be able to create seeds. So these are the two factors we're trying to balance. The probability that we die if we wait too long, and the amount of seeds we can produce by growing for a longer period of time. Now the way that we would do this with mathematical modeling is we would consider each of these factors as a function. So our first function might be the probability of death. Actually, let's think about it in the reverse. The probability of survival. So we're going to calculate the probability to survive as a function of time to reproduce. So here I'm going to have my variable t, and I'll have some function that's my survival. So let's call that some function survival of time. Actually, I don't want to use s because I want to use that for my total number of seeds. So let's call this maybe Greek letter sigma for survival. And the idea, the longer I live, my probability to survive is going to go down. So I want some function that decreases, and the longer I live, the smaller my probability of survival. So this is one of the factors that's decreasing as a function of time. In fact, let's write that down. So this function that represents our survival, it's a decreasing function because the longer we live, the lower our chance for survival. On the other hand, we have our second factor. So let's create a second graph. Again, we're going to have our age at reproduction. And this time it's the number of seeds. So the longer we live, the more seeds we can produce. So this is going to be the number of seeds that we can produce. So if I have this idea that the longer I live, the more I can produce, this function should be some sort of increasing function. So let's give this a name. In biology, the number of seeds is often called the fecundity. So we'll use this symbol F for our number of seeds, and this function needs to be increasing. Now I've just drawn some pictures of functions that are increasing or decreasing, and the idea that would happen in a more careful mathematical model is that we could measure these. So we somehow measure the survival probability by taking, experimentally, maybe we have 1,000 plants, and we just keep track of how long they live based on their age. Similarly, we might be able to have an experiment where we could control the time at which a plant generates its seed, maybe through environmental controls, and then we can measure the number of seeds that it produces based on, more likely than time, we'd probably measure it versus its size, and we could create a relationship between the body size and the number of seeds it produces. To get this relationship to time, we would need to have a time to body size correspondence. But for us, right now we're just going to be thinking about these two functions, the probability of survival and the number of seeds that we produce. Once we have a relationship for something specific, we can do some calculations. So here I'm taking a particular assumption. So here my survival function of time I'm thinking of as an exponential decay, so e to the minus at. And that function would be a nice exponential decay function that represents my survival. I also have my fecundity function that I'm modeling with time that's a power function. So here we're thinking of some constant times the time to a power. This is my relationship for the time at which I reproduce and the number of seeds I can create. And depending on what that C looks like, if that power C is something less than 1, I might get a curve that looks like this. It's increasing. On the other hand, if my power is greater than 1, it might look more like a parabola or a cubic or something. But I have some relationship between these two functions. And you can see that the function S is a product of my survival function times my fecundity function, and this new function S is the average number of seeds given our strategy, average number of seeds. Now in biology, an organism wants to maximize its fitness, which is maximize the number of offspring it has. So our goal for optimizing is to maximize our function S of t. Well, how do we do that? We use calculus. We find critical points first by calculating the derivative. And so our derivative of our function is a product rule. So we'll get negative a e to the minus at is the derivative of the exponential. Leave the power function for our fecundity alone. Plus now we'll leave our survival function, but take a derivative of our power function. So b times t to the c minus 1, I forgot to say the times c, this is my derivative. And I want to find critical points of the original function. So critical points of our average number of seeds are where the derivative equals 0. So as we're doing that, it helps to think about always factoring. So this is an important strategy. We always want to factor this. So let's look and see what common factors we have. Both of our terms have the exponential. Both of our terms have this constant b. And then we have powers of t, and the power c minus 1 is the common factor. So now let's rewrite our derivative. In factored form, we get b times the exponential. We have t, c minus 1 powers are in common. And what we have left is negative a times t in order to get my power c, and then plus c for the second term. And our derivative equals 0 leads to, in fact, two critical points. So the exponential part can never equal 0. Exponentials are always positive. The power of t will lead to a critical point at t equals 0. And then the other factor, negative at plus c equals 0, will lead to a critical point of t equals c over a. So these are going to be my two critical points. I can use the first derivative test for extreme values. Our critical points are 0 and c over a. And we can pick values in there and decide what's going to happen. Now, all of this first factor for positive t, that's going to be a positive number. So all that's affected is the second factor. And when t is 0, I get 0 plus c, so that factor will be positive, and it doesn't change sign until I cross when t is bigger than c over a, in which time this term negative at will be bigger in magnitude than c, and we get negative. And so this is actually where we have a maximum. So this tells me what my optimal strategy should be. The plant should grow until there's this time when c where the time is equal to c over a for this model. Now this could be tested experimentally. We could look and see if that is the time at which the plant reproduces, and that could actually be done in a laboratory. Now let's consider the second situation, the search versus exploit. Imagine that I'm a bee, I'm collecting pollen, and I spend some time in a patch. If I stay there too long, eventually I'll run out of resources. So I'm going to need to travel to another patch and be able to start the process over again. Now, I don't want to spend too much time where I'm gathering smaller amounts of resources if I could travel to a new patch and be getting a lot more. So what are the competing factors? Well, if I stay at a patch, I gather more resources. And the currency of animals, collecting food, is really collecting energy. So the longer I stay at a patch, the more energy I collect. But the problem is, the longer I stay at a patch, I'm collecting my resource at a slower rate. In the language of calculus, my rate of collection refers to the derivative of my energy that I've collected. And to say that my rate of collection is decreasing is talking about a second derivative. So if I think of E as a function of time, this is the total energy that I collect if I exploit my resource for a time t. So the first idea, the fact that the longer I stay, the more I collect, that's telling me that my first derivative is positive. I'm increasing. But to say that the longer I collect, that my rate of collection itself is decreasing, is saying that my second derivative is negative. In other words, my function is concave down. So notice what we've done. We've taken some biological assumptions that the longer I stay at the patch, the more energy I collect, but my rate of collection is decreasing, and I've converted that into some mathematical assumptions about my function that represents the total energy I've collected as a function of time. So let's draw what a typical picture would be. My axis t is the time that I spend exploiting the resource, and the vertical axis is the total energy I've gathered. And of course, if I don't spend any time at all, I should collect no resource. But if I spend some time, I start to collect my resource, but this function needs to be concave down. And so this picture being concave down is sometimes called a law of diminishing returns, that the more you commit to gathering resources, the less you're getting each unit of time. So you don't steadily gather the same amount of resources. The longer you collect, the less you get per unit time. Now, we could have functions that we actually use to describe that. So, for example, we could use something like a Michaelis-Menten form. So, expected, or the energy collected might be some parameter times time divided by the time plus a half saturation value. Or there could be some other function. I'm not really specifying what kind of function I have, but there is a function for the total energy I collect that's increasing in concave down. And the cool thing is we're going to be able to say something about the optimal decision without necessarily choosing a particular function. So with this new slide, I've summarized some of our key points. Little t represents the time I spend exploiting a patch, and there's a function, the energy gained, that is increasing in concave down function of that time I spend. And if I thought about what the organism wants to optimize, it's not optimizing an instantaneous thing, it's somehow optimizing over the whole day. And so we want to choose a strategy that maximizes the average rate gained per day. So I'm going through these cycles of gather resources followed by hunt for a new patch. And so each cycle I collect E of t, but the total amount of time it took to do that is the time finding patches plus the time exploiting. And so this is the function that I'll want to optimize. This is somehow an average rate of energy, an average rate of energy gain. Well, how do we find optima, or extreme values? We calculate the first derivative. So here we have a quotient. So we're going to use the quotient rule. Low-D high, that's t plus little t. times the derivative of the top minus high d low, so that's the energy function, and the derivative of the top, or the bottom, d low, is 1, and then we'll do t plus little t squared. And we're interested in at what time will this be equal to 0. So a fraction is equal to 0 when the numerator is equal to 0, and so I get that we're looking for a time where the first derivative times the quantity spent hunting and gathering minus our total energy gained, that's equal to 0. And I'm going to factor it, or solve for the derivative. We're looking for a point, so we look for a point so that the derivative of e is the same as the function divided by the total time. This is what we're trying to identify. And the cool thing is that this has an interesting excuse me, geometric interpretation. If I were to graph, let's see, I'm going to think about my function e of t, some increasing concave down function. So this is e of t, and this is my t-axis. And so this, the origin corresponds to the time when I first start start exploiting my resource. So there's some time capital T, so this is time minus t in the past. This is when I started looking for the patch. So look for the patch. Here's when I find the patch. And then I start to gather resources. And this ratio that we're calculating is actually a slope. It's the slope joining two points that are here at negative t0 and some other point which is at t e of t. So we're calculating the slope e of t minus 0, which we don't need to write, over t minus negative t is the slope. And what the solution is saying is that we are looking for a point where the tangent line slope matches the slope that we just found. In fact, I happen to have picked that point. So here, this tangent agrees with the average. If I picked a different point, so for example, if I went to this point, my slope of my tangent line and the slope of my average don't agree, so this is not the optimum. So somehow this is the special point, and this is the optimal time I should spend gathering resources. And in the textbook, this has a special name. It's called the marginal value theorem. Now, I'm not going to expect you to learn and remember the marginal value theorem like I do some of the other calculus theorems, but it's an interesting application that if I want to maximize the average rate of gathering a resource, that somehow I'm looking for a point where the tangent line is the same as this average line, which is a really cool result. And I think this is one of the great successes of mathematics and biology working together. This again is something that can be tested experimentally. In fact, the textbook has some discussion about birds that take time to get to a resource and then they start to collect the resource. And experimentally, the scientists are able to control how long it takes for the birds to reach the food. And they can measure how long the bird is spending eating food at a certain spot before it moves to a new site. And with a lot of success, this theory predicts when that bird is going to make that transition. So I think this is just a beautiful result, that mathematics and optimal values are actually leading to real results of decisions that organisms are making to lead to optimal outcomes.